Okay, so moving on with vectors. Previously we talked about properties of vectors. We looked at dot products, we looked at cross products, we looked at applications. Our focus in this section is going to be to describe lines in terms of vectors. We're going to look at just a curve or two written in terms of vectors, and then we're going to move on to calculus properties like limits, derivatives, and integrals. So let's go ahead and look at lines in space. When we describe a line in space, now this is in three-dimensional space, we need an x, a y, and a z coordinate because we're in three-dimensional space. And typically to describe a line, you need a point on the line and you need its slope. Well, that's easy to do with vectors because let's look at this line here, highlighted in green. And let's look at these 2 points. Okay, we'll look at this p sub 0. This would be like our starting point. Notice that this is actually the head of a vector whose tail is at the origin. And we'll call this vector r sub 0. Now let's look at another point, P, on our line, which is going to be the head of this other vector r. When we look at the vector between P sub 0 and P, this is what's going to be our direction vector, and that's going to take the place of the slope of our line. So to describe a line in terms of vectors, we need an initial point and we need a direction vector. So that would be what's inside this box right here. Okay. So our equation of our line r is going to be equal to the initial vector r sub 0 plus t times our direction vector. That's a little bit difficult to use, so inside this box there's going to be the formula that we're actually going to use. So remember, we have an initial point on our line. What that point becomes is that becomes a vector. It becomes the head of our vector with tail at the origin. And then we have our direction vector v, and that becomes t times our direction vector. And that's it. That's how you describe a line using vectors. But remember, this line goes on forever and ever and ever, so we're really looking at t values from negative infinity to positive infinity. Now going back to our parametric form, x is equal to x sub 0 plus at, y equal to y sub 0 plus bt, and now we have our z coordinate, z equal to z sub 0 plus c times t. Where that comes from is that comes from our initial point, p sub 0. So you see the x sub 0, y sub 0, z sub 0. And this a, b, c, the direction vector, remember that was replacing our slope. Example 1, we're supposed to find the equation of a line that's passing through 2 points. And or going through 1 point, sorry. And then we have our direction vector. In part B, it just says to find the projection of the line onto the xy plane. So let's look at A. Well, we know we're going to have the equation of the line written as a vector in terms of the variable t. So I need my vector through my point, so this would be like my x sub 0, y sub 0, z sub 0, this negative 1, 2, 5, so that's just a vector, negative 1, comma 2, comma 5, plus our variable t times our direction vector, which is given to us, that's our vector v, that would be your a, your b, and your c, 2, comma 3, comma negative 5. And I'm actually done. So super simple. But normally we don't leave it this way. We would distribute the t, and then we would add these two vectors together. So it's going to be negative 1 plus 2t, or negative 1 plus 2t. That would be the first component. And then 2 plus 3t would be the next component in my vector. The last component would be 5 minus 5t. But remember, this is a line, so we need to specify that our t values are going to go from negative infinity to positive infinity. That would be it for part A. Let's look at part B. So part B says to find the projection of the line onto the xy plane. Well, first of all, what does that even mean, the projection of the line onto the xy plane? What that means is you set your z value to 0. We're not looking at the z value at all, we're getting rid of it. And we're just looking at the line, the equation of the line, if it were just in the xy plane, so in two-dimensional space. So again, when we say xy plane, the projection on the xy plane, that means that we're going to let z equal to 0. And all I have to do is look at my parametric representation. That means my x value is going to be equal to x sub 0, which was -1, plus a times t. A is 2, so plus 2t. And my y value is going to be 2 plus 3t. So that's the equation of the line in the xy plane. But typically when we look at the projection of the line onto the xy plane, we describe it in terms of x and y, and we get rid of our parameter t. So this is what we did in chapter 12, if you recall. The easiest way to get rid of your parameter t is to try to take one of your equations and solve it for t. Looking at my x and y equations, neither one looks really good. So what I'm going to do is I'm going to take my equation x and I'm going to solve it for t by adding 1 to both sides, dividing by 2. Then I'm going to take that t value and I'm going to substitute it into my y equation, which gives me y equal to 2 plus 3 times x plus 1 over 2. And that would be the equation of the line in the xy plane. And of course I would never leave it like that. I would go ahead and distribute this 3, or 3/2, so that becomes 3 over 2, 3 over 2x plus 3/2, and then combining like terms, we have 3 over 2x plus 7/2. And this would be the equation of our line in the xy plane, or the projection of the line onto the xy plane. So sometimes I do these examples just so you know what they're asking for when you look at the questions on My Math Lab. In example 2a, we're asked to find the equation of a line passing through 2 points. Notice we don't have a direction vector, so we have to find the direction vector. And then part B says find the equation of the line segment with the endpoints P and Q. So these points are the same. Now when you're given 2 points and you have to find the equation of the line, it doesn't matter which point you choose to be your x sub 0, y sub 0, z sub 0, unless it says a direction. Like if it's going from P to Q, then P would be that initial point. So I'm just going to randomly let P be my starting point. This is my x sub 0, y sub 0, z sub 0, or x naught, y naught, z naught. But again, I could have easily chosen in this particular problem to let Q be my starting point. So remember, I need a direction vector. The direction vector is going to be the vector P to Q, which means I'm going to take Q and I'm going to subtract P. So 4 minus a negative 2 would give me a positive 6. 1 minus 0 is positive 1. And then -1 minus 7 would give me a -8. So this is my direction vector. This is like your A, your B, and your C. Thus the equation of our line in vector form would be my initial, -2, 0, 7, plus t times my direction vector, 6, 1, -8. And again, I wouldn't really leave it that way. I would combine the two. And when we combine this, we get -2 plus 6t, 0 plus 1t, so that's just t, 7 minus 8t. To indicate that this is a line, I would also state that my t values are going to go from negative to positive infinity. So this was our part A. And then when we look at B, part B, we're using the same points. This says to find the equation of the line segment with endpoints P and Q. Okay, so now we're not going to look at t values from negative infinity to positive infinity. We want to figure out what t values give us the endpoints at -2, 0, 7 and 4, 1, -1. Well, notice if t is 0 in my equation, I get -2, 0, 7, right? So I know that my t values are going to start from 0. My equation's going to be exactly the same. All I'm doing right now is just adjusting my t values so that this is a line segment, not the complete line. Okay, so 0. Now I need an ending t value that gets me to the point 4, 1, -1. Well, if t is equal to 1, and here you could do this algebraically, but I'm just looking at my equation R, and notice that that y component is just t, so I want that to equal 1, which means I'm going to replace t with 1, and it works out. So our first component would be -2 plus 6, which would be a +4, 1, and then the last component, our z component, would be 7 minus 8, which is -1. So just be careful on what you're being asked to find. Are you being asked to find a line segment? Are you being asked to find a whole line? We'll do another example. Example 3 says to find the equation of a line, and we have a point that it's going to go through, -1, 0, 5, and parallel to this given line. Okay, so since these lines are going to be parallel, I can use the same direction vector. In this equation RT, what I'm going to do is I'm going to break it into its components so I can identify my direction vector. So 5t is the same as 0 plus 5t. -9 plus 3t is the same as -9 plus 3t. Okay? And then -4t is the same as 0 minus 4t. So I'm just breaking it up into a point and a direction vector. So I'm going to put all the t's in one vector and everything else in another vector. So this would be 5, comma, 3, comma, -4. So you can double check by distributing the t and combining those two vectors with addition, and we should get back to our original vector. So the whole point is to figure out my A, my B, and my C. My equation is going to pass through the point -1, 0, 5. So it's going to be the vector negative 1, 0, 5. And I'm going to add it to the same direction vector. Right? So the only difference between these two is it's passing through different points, but they're going in the same direction. These are parallel. And then I would just combine this to write this as negative 1 plus 5t, 0 plus 3t, 5 minus 4t. And this was a line, a complete line, so negative infinity to positive infinity. Sometimes my lab will leave off the negative infinity to positive infinity. In general, if it's not there, we can assume that it's all t values. Okay, so now what we're going to do is we're going to talk about curves in space. When we talk about curves in space, we're not going to really get into defining our curves in terms of vectors, which we can. We're just going to look at an example where it's already defined for us, because it's very difficult to define curves in terms of vectors. The reason being that, and let's look at this curve here. As I go along this curve, notice that the direction changes. When we were writing the equation of a line in terms of vectors, we needed a point, we needed a direction vector. And since the slope of the line, or the direction of the line, doesn't change, that was sufficient. Unfortunately, if a graph curves, the direction is constantly changing. So the question becomes, how do we describe this when the direction is constantly changing? Well, in most cases it's very difficult. So instead of describing functions in terms of vectors, curves in terms of vectors, what we're going to do is we're going to look at some curves that are already defined, and then we're going to use properties of functions and apply them to these vector valued functions. We're going to look at domains, we're going to look at limits, we're going to look at derivatives, and we're going to look at integrals. So first of all, when we do look at a curve in space, and we describe it in terms of a vector valued function, the components are going to be functions of t. So you can think of this as being sort of the x value, the y value, and the z value. They're all functions of t. A vector valued function has positive orientation, and this is the same as how we described it in chapter 2. That would be the direction that the curve is generated in as our t increases. But now, since we're talking about functions of t, it's appropriate to talk about the domain. So when we look at the domain of a vector valued function, what we're going to do is we're going to figure out the domain for all of its pieces, its 3 components, and we're going to look at what those 3 domains have in common. So the domain of R is going to be the intersection of all of these domains. Example 4, we're given a vector valued function in terms of the unit vectors I, j, k. You can think of this t squared as being your f, the square root of t as g, and 1 over t minus 7 as h. I'm going to use some shorthand for domain of f. That's just t squared. So when we're talking about the domains, first of all, we're talking about t values. We're talking about values we're putting into our function. Since it's t squared, I have no restrictions. I can put any real number into t squared. So the domain is going to go from negative to positive infinity. When we look at the domain of g, the square root function cannot be negative. It can be 0. So I'm going to use a bracket, and it could be any positive number, but it cannot be negative. So the domain of g is going to be a bracket with 0 to infinity with a parenthesis. The domain of h is a rational function, it's a fraction. Fractions are undefined when their denominator is 0. So I can see that if t is equal to 7, I'm going to have a problem. But I don't have a problem with any other t values. So I can use any t value from negative infinity to 7, but I cannot include 7, so that's a parentheses. Or, which would be my union, I can choose from 7 to positive infinity. Now the domain of my vector valued function r is going to be the intersection of all three. What do they have in common? Well, that would be 0 to 7, 7 to infinity. So again, to find the domain for a vector valued function, you have to look at the domain for all of its pieces and look at what they all have in common. Example 5, we're going to find the domain of our function, r. It's 3 cosine of t I plus 2 sine tj plus 1 over pi k. We're also going to describe the graph. So the domain, I need to figure out the domain of all of its pieces. So f is going to be 3 cosine t, g will be 2 sine t, and I'll call h 1 over pi. The domain of f, well, cosine is continuous for all values of t, so negative infinity to positive infinity. The domain of g, sine continuous for all real numbers, so negative to positive infinity. And the domain of h, well, that's just a constant function. I could put any t value I want into that. So it's kind of easy to see that the domain for our vector valued function r is simply negative to positive infinity or all real numbers. And now comes the weird part, describing the graph. Well, I don't know what this graph is, but I do notice that the h component is 1 over pi. That's just a constant. So sometimes it's easier to describe a three-dimensional object by first looking at its picture in the xy plane. So imagine looking down on your function. So in order to do that, I'm going to go ahead and let the z value be 0. So that means I'm going to describe this graph just in the xy plane. So I'm looking at the projection onto the xy plane as we did in that previous example. So first of all, if I look at these components as, say, my x value 3 cosine of t and my y value as being 2 sine of t, because this is an xyz, right? We get points on a curve in space. And now remember the z value, I'm letting that be 0. So something to note is that there's a cosine and a sine. That reminds me of a circle. The problem is that it's a 3 cosine and a 2 sine. They don't have the same coefficients, so I don't think it's a circle. But if I looked at x squared, that would be 9 cosine squared t. And if I looked at y squared, which is 4 sine squared t, I know with my unit circle that x squared plus y squared is equal to 1, right? But my x squared is 9 cosine squared t, plus y squared is 4 sine squared t. So that's supposed to be equal to 1 on a unit circle. Well, if I simply divide out by 9 for the x squared and divide out by 4 on the y squared, then I get cosine squared plus sine squared is equal to 1. So that's sort of a roundabout way to get the equation of an ellipse. Remember, this is just in the xy plane. So in the xy plane, we have an ellipse. And the center of this ellipse is at the origin. I'm going to sketch a graph. And it's going to be a three-dimensional graph. I'm going to sketch the ellipse in the xy plane. So that would mean, because the 9 is under the x squared, that means I'm going to go out 3. That would be like an a squared in the general formula of an ellipse. So I'm going to go out 1, 2, 3. And then the other way, 1, 2, 3, right about here. There's a 4 under the y squared, so that tells me I'm going to go 2 units on the y, 2 units back this way. And here I have my ellipse in the xy plane. So now let's go ahead and talk about what that z value 1 over pi means. Think about this. As I put in t values, so let's say that I'm where z is equal to 0. As I put in t values, I'm going to be going around and around, but I'm going to keep adding 1 over pi for my z value. What this turns into is what we call a helix. Okay? So we start out, and as my t values increase, I'm still going in an elliptical pattern, but I keep adding 1 over pi to my z value. So it keeps going, and it goes in both directions, right? We also can go down from here. Now this is a spring. It looks like a spring, right? So maybe we could say that this is an elliptical spring. And if you've already had a lot of physics classes, you might also recognize this as being a helix. So helixes do come up quite a bit. That's why I wanted to go over the graph of a helix now. All right, so let's move on to some other properties of vector valued functions that correspond with properties of our functions with x and y. One of the things we talked about with functions is we talked about limits. So when we say the limit of a vector valued function, that would be just a vector, as opposed to a real valued function, which would just be a function with x, y, and z. All right. So our vector valued function r approaches this limit. So something I want you to notice is that this limit is a vector. We're working with vectors. As we take limits and derivatives and integrals of vector valued functions, they're all going to be vectors. Okay? So a vector value function approaches our vector limit, and we write it the same way we write limits, the limit as t goes to a of r of t is equal to L, provided that the absolute value of their difference is equal to 0. So that's going back to our definition of a limit from Calculus 1. So let's just say we do have this vector valued function written in terms of its vector components, or we could write it in terms of ijk. Well, if we take the limit of each component, that's going to be the limit of r as a vector. So we talk about limit, what goes with that is this idea of a continuous function. It turns out that our vector valued function is continuous at some value, provided the limit is equal to the value of the function. To go along with that, we have this theorem that says if f, g, and h are continuous, or f, g, and h are continuous if and only if r is continuous. So if you know that your vector valued function r is continuous, then you know each of its components is continuous. On the other hand, if you know that all of the components are continuous, then the function itself is going to be continuous. So again, these are similar to properties that we've seen in calculus. Now we're just applying them to our vector valued function. So let's go ahead and evaluate limits, and we'll just do a few of these. Example 6, we want to evaluate the limit as t approaches pi over 2. My vector valued function is 3 cosine ti plus 2 sine tj plus 1 over pi k, which is the helix that we looked at previously, and we looked at its graph. So I tend to like to write my vector valued functions in terms of the components, say 3 cosine of t comma 2 sine of t comma 1 over pi, because it's easier for me to write the limit. So the limit of r as t approaches pi over 2 would be a vector, where all we have to do is take the limit as t approaches pi over 2 of each of the components, so 3 cosine of t. So we're going to take that limit, and then the limit. So it's like you're distributing the limit. The limit as t goes to pi over 2 of 2 sine t, and then the limit as t approaches pi over 2 of 1 over pi. So the limit as t approaches pi over 2 of 3 cosine t is 0. Remember, the limit is a vector because it's a vector valued function, so that would be 0 comma. The limit as t approaches pi over 2 of 2 sine t is 2. And then the limit of a constant is just a constant. So the limit as t approaches pi over 2 of 1 over pi is simply 1 over pi. And that's it. So that's the limit of r as t goes to pi over 2. But there's another part to this example. It says, is r continuous at pi over 2? Well, we could use that theorem at the end. We already know that the limit as t approaches pi over 2 of r is equal to 0 to 1 over pi. So remember, it says that if the limit is equal to the value of the function, then it's continuous. If we put in pi over 2 into our vector function, we get 0 to 1 over pi. So since these are equal, then that means that r of t is continuous at pi over 2. So that's all you have to do for continuity. is just to check to see if the limit is equal to the value of the function. And again, that's exactly what we did in Calculus 1. Ooh, that's a little bit big. Let's go ahead and look at one more limit. Example 7, we're going to evaluate this limit as t goes to infinity. That's going to irritate me, it's huge. As t goes to infinity of e to the negative ti plus t over 2t minus 7j plus 7k. So let's take the limit of each piece. So again, you could write this as a vector, or if you don't feel like writing it as a vector, you have to sort of distribute this limit to all the pieces. So that would be the limit. So this is just proper form. As t goes to infinity of e to the negative ti, because it's a vector, plus the limit as t goes to infinity of t over 2t minus 7j plus the limit as t goes to infinity of 7k. Again, the limit of a vector is a vector, which is why I'm leaving in the I, the j, and the k. If we look at this first limit, as t goes to infinity, remember this is the same as 1 over e to the t. So just a reminder that this is the limit as t goes to infinity of 1 over e to the t. So as t goes to infinity, the denominator keeps growing and growing and growing, so this fraction is going to be approaching 0. So this is simply 0i plus. As t goes to infinity here, we get infinity over infinity. So remember, we have these indeterminate forms, and I'll write it above here, that we have to be careful about. Indeterminate means we cannot determine the limit. We have to do something more. So our indeterminate forms would be forms like infinity over infinity, or negative infinity over infinity. 0 over 0, that's another indeterminate form. 1 to the infinity, 0 to the 0 power, 0 to the infinity. Oh my gosh, there's so many. How about infinity minus infinity? These are all indeterminate forms, meaning we cannot determine the limit. We have to do something more. So in this middle limit on the j component, it's going to be infinity over infinity. So what we've done in the past is we've either used L'Hopital's rule if we get any of these first two cases. Remember, we could use L'Hopital, which means take the derivative top and bottom and reevaluate. Or we could algebraically divide all these terms by t. If I divide all these terms by t, I'm looking at the limit as t goes to infinity of 1 over 2 minus 7t. Now when I reevaluate that limit as t goes to infinity, what's going to happen is the 7 over t, that's going to go to 0. So it's going to be gone, right? And that will just be 1/2. I wasn't going to write it, but I think I am going to write that. So this is just going to be 1/2, and I forgot my j. Now looking at this last piece, the limit of a constant is a constant. So this limit here is going to be 7k. When we put this together, the 0I I don't have to write. This limit is simply 1/2 j plus 7k. I only wanted to do that example so that we can go over some indeterminate forms. Now remember, you don't have to keep things in IJK form. You can always go ahead and write it in vector form. Just remember that now our I is 0, so it's simply 0, 1/2, 7. And that's it for this section.